Marvin OGORE is a student from the University of Rwanda, and his talk is about modeling and simulation of edge AI inference for instantaneous offline prediction of cholera in rural communal water taps. And Marvin, the floor is yours.
I'm Marvin. I've been working with Dr. Jimmy and Dr. Kizito. I'll be presenting offline prediction of cholera in rural communal tap water settings. So I am coming from the African Center of Excellence in IoT. It is hosted within the University of Rwanda. It was launched in 2017 thanks to the help of World Bank, and it is aiming to bridge the transferring of IoT-based research innovation from academic research to African industry. So it's basically trying to bridge the gap between the academic settings and the industrial setting. So the main activities are capacity building from programs of master students and PhD researchers and international collaborative research projects. So currently 3 master students and 1 PhD student. So I'll introduce my use case, which is cholera warning on communal rural water taps. So the motivation for the studies was based on societal challenges that were identified and the existing technology that was lacking. So in Africa accounts for 54% of the cholera disease burden, and cholera is a water-borne disease that kills up to 200,000 people yearly. And we see Africa as carrying the load compared to the rest of the world. So the detection technologies that are used to detect cholera are they're not cost effective and they're not scalable for mass deployment. This is because they take very long. They use reagents such as alkaline peptone water, which is abbreviated in the slide as APW, so that it can take up to 24 hours to detect cholera, and they require lab settings. So our research basis was looking at these deficiencies, and we were targeting communal rural water taps in Africa, and we wanted to apply edge AI cholera pluggable detection devices to these existing rural communal water taps. So to do away with the existing technology that is using laboratory settings and taking too long, which makes it not scalable, you can use edge AI to do away with these deficiencies. So the approach would be to use data, which is physicochemical properties of water. So we're looking at the chemical properties of water that allow cholera to exist into the water. This would make it cheap for mass deployment because we have very many taps that are located within the rural setting. And we chose edge AI because of the poor rural internet connectivity that is in rural settings in Africa, and also for a fast response time in order to deal with the disease burden that is caused by cholera disease. Moving on, so we were designing our design approach is as follows. We will be using physicochemical properties of water, as I had mentioned. So for our research, we identified open dataset sources. One of them was based in Katana Health Zone that is located in Rwanda. They were measuring physicochemical properties of water and the existence of and the cholera cell count in water in Lake Kivu. So they were measuring how the existence of cholera in water, and then they measure it against the against temperature, turbidity, pH value of water, conductivity, and salinity. These are the 5 chosen physicochemical properties of water because they support the existence of living organisms in water as it was identified from our background research. So these data source, these sensors will be fed into an embedded microcontroller unit. We were also hoping to embed with LEDs. So the red LED will tell you whether the water is contaminated. That is, yes, there's cholera in the water. We also have a yellow LED because we're also looking at an environmental approach. We also be able to identify whether the water is of quality for drinking, aside from disease detection. And the green LED will be able to tell us that, yes, the water is now safe for drinking. So to be able to achieve this, we'll also have an SMS sent to a local health official or a local coordinator. So we have a GPRS existing systems in the rural areas in Africa. So that was the chosen means of alerting in our research approach. So we onboard a machine learning via TinyML. And to achieve this, we would have the open data source fed into an edge AI stack where training and TinyML generation would happen. And then for our situation, we were targeting to deploy this into an embedded simulator, and then we will carry out inference to say whether we have the water is cholera safe or it is not safe. In my next slide, our edge AI rapid prototyping tool stack. So what we identified from our research is that existing data, we have very little data sets for cholera. That is very limited data in terms of having physicochemical properties that are measured against cholera cell count in water. So this was another challenge. So how do we tackle this challenge? Our approach would be to use synthetic data generation toolsets. We identified one called as mostly generate, which will look at the trends of the existing data. You feed it into the synthetic data generation tool. After you've synthetically generated data according to the trends of your existing data, you feed it into, you separate it into training data and test data. The training data will be used to gain experience and insight that will be used to carry out inference on a later on stage. The training data is uploaded into an edge AI platform, that edge AI as a service, and the test data will also be uploaded into the same platform. Our chosen edge AI as a service platform was Edge Impulse. It provided us an easy way to prototype our existing solution. The basis of this research was to be able to carry out without having any, the only challenge we would have was maybe the existing tools we would have. We were aiming to do our research with the available tools that were at our disposal, and Edge Impulse provided this rapid support. And at Edge Impulse, we were able to carry out our training, and we were able to have our CMSIS pack for STM32 microcontrollers. This was a library that was adopted and was targeted for STM32 boards. Later on, this library was embedded into an STM32 cube, that is an Edge AI application IDE for STM32 cube for STM32 devices. And afterwards, after you've gotten your code and you've compiled, we were able to deploy this on an embedded simulator. The chosen embedded simulator for this instance was Proteus. And from there, you can be able to load your test data, or you can load your real world test data and carry out inference and get your results. So for the simulation layout, this is just a pictorial depiction of what was going on in the background, more into the technical details of what was happening. So you can see from the left-hand side is that this is the STM32 IDE, STM32 Cube IDE. This is where we got our library from Edge Impulse, our CMSI pack. And it was after you build this, you're able to have a build analysis. You're able to know how your model will perform on a real life existing board. So you can see from our instance, we had a RAM of 64 kilobytes and a flash of 128 kilobytes. Our target board was an ARM Cortex M4 core with DSP and FPU 512 kilobytes of flash memory. So from the build analysis, this will be able to fit into our target boards. This, after building, you will be able to generate a hex file that will be loaded to our Proteus simulator. So the chosen board was an STM32F401VE. This will, you can be able to rapidly fill in the components into a Proteus simulator. You connect the devices. So we chose to have an LCD so that we can be able to carry out inference from our test data. Remember this, we were not doing any, we did not have any hardware components. So we were just trying to simulate and see what would happen if we had hardware devices. So we were rapidly prototyping to see how to simulate how a real world hardware device will behave. And we successfully loaded Proteus PCB layout components with LCD. We first carried out the test with a virtual terminal, and we later on decided to put an LCD. So this was for easy visualization, also for the target consumers of water. And we did this research with the native neural network on edge impulse, but our background research showed us that our machine learning techniques such as support vector machine perform better when you're performing water quality analysis. So for low data sets also, support vector machine from our background research shows that it outperforms native neural networks. So we applied this on Edge Impulse, where you can go into Edge Impulse and actually have an expert mode instead of a graphical additional of layers. You can actually have an expert mode and load your Python code into Edge Impulse and carry out your training and get the results. So from the results that we've gotten is that SVM outperforms native neural networks for small data sets. Remember, we had a challenge of data sets, and we were looking for a machine learning technique that will be scalable for small data sets. So for the results, we got a model inference performance of 94.03%. This is after tweaking the hyperparameters of the neural network and hyperparameters of SVM. The parameter grid will be including the C and the gamma, and you also implement a kernel RBF specific for support vector machine. This is a graphical graph that will show you the accuracies of support vector machine against a native neural network provided by Edge Impulse. We will also see that Edge Impulse provides you a way to see how the model will perform. It will optimize the model and give you results such as RAM usage, latency, which includes how long does it take for you to get an inference result from your existing model. And the ROM usage is 15.1 kilobytes with an accuracy of 94.03%. So the confusion matrix you got was, it was able to detect for no cholera, yes, cholera. We were also able to detect for anomalies, that is to say, if it is not, the temperature or salinity is not within the range for which we trained it for, we'll be able to detect this as an anomaly, which will be used for future insight to look at how this is can be related into machine learning techniques. So on-device real performance metrics would be 1 microsecond and a RAM of 1.5K and 14.9 kilobytes. These results were gotten from a Proteus simulation suite is able to also give you on-device real-time performance metrics for your device. These were the results that we captured for our research, and the achievements that we were able to get were a simulation of an edge impulse generated model on Proteus. So we are able to show that before you actually deploy your device on an actual hardware, you can be able to simulate and see whether your research will be feasible. It will be able to give you insight on specifics such as targeted microcontrollers. Are you getting the right metrics for your microcontrollers? Is it able to achieve the same accuracies that you wanted to achieve on an embedded device? We were able to achieve an AI model for prediction of cholera on embedded device. So it is also good to note that most AI models perform water quality analysis. They've not been designed for disease detection. And also to add on to our research would be that we are performing this at the edge. We are actually targeting rural communities. We are targeting areas where the network is poor. And we are also able to achieve a cheap real-time detection of water. We were able to do away with labs. We were able to do away with expensive raw materials that are needed. From our background research, we saw that they had PCR tests that are very expensive for resource-constrained countries in Africa. And we were able to also achieve synthetic data generation. So from our TinyML chapter in ACIoT, we are able to pipeline all of these procedures such that any new person who comes into the research, you'll be able to see the tools that we used, and you're able to integrate your use case accordingly. This is due to limitations of time. This is what I was able to present for you today, and thank you so much for your time. We welcome any comments and questions.
Thank you, Marvin. A very interesting problem we are trying to tackle. There is one question in the chat. So it's from Christian Tennessee. He asks, how does cholera affect water differently than other less dangerous microorganisms? If you try to differentiate between cholera-infected water or water infected from other microorganisms, and if your method can get false positives.
Yes, okay. So for our research, we were mainly focusing on cholera. I understand this question is asking if you're able to differentiate between cholera and other microorganisms. So the existing thresholds for other microorganisms may vary depending on what you're trying to detect. So this was a very interesting approach, looking at the unique physicochemical parameters that are unique to cholera itself, instead of having it unique to other microorganisms. Also, we chose to use physicochemical properties because of there are different techniques of detecting the other kinds of microorganisms. So cholera was interesting because it will also give you an insight on the amount of fecal matter in the water. So they are closely related. So the amount of fecal matter in the water will be able to tell you whether the water has cholera or not. So there might be an overlap in some situations, but we chose to show that we can actually do disease detection without laboratory settings. So this was the target of the research.
Okay, thank you, Marvin. I think you answered the gist of the question.
This would not be made possible without our sponsors, whom I would like to once again express our gratitude, starting by premier sponsor Newton.ai. Thank you guys so much. The executive sponsors, which involve ARM, Edge Impulse, Qualcomm AI, and Sentient. The platinum sponsors, which involve Infineon, Reality AI, the gold sponsors, which involved Latent AI, SenseML, and last but not least, our silver sponsors, which involve EMSA, Greenwaves, Kixo, Imagimob, HOTC, Seed Studio, and ST Microelectronics. Thank you, everybody. See you all tomorrow with more exciting features.